Hello, today we will be working on the same symmetric frame, but we will solve it in a different way. Now let me draw it. Let's remember the frame one more time. I have this pin supports here. It's under gravity loading 12 kilonewton per meters. This distance is 6 meters. And that distance is 3 meters. And let's label A, B, C, and D. Okay, now, as we said before, that's a symmetric frame under symmetrical loading. So we have a symmetric structure under symmetric loading. So having these in mind, we expect to see a symmetrical deformed shape, right? This is why should it be different. And also we expect to see a symmetric moment diagram. So we said that, okay, in this structure, that's our symmetry axis. So whatever I see on this side, I should see the mirror image on the other side. So let's draw the deformed shape. So we expect to see a deformed shape like that. And the mirror image on the other side. And what we know about this deformed shape is, since it's symmetric, in order to have a symmetrical deformed shape, this rotation must be equal to 0 at the middle. Okay, so knowing all this additional information about the deformed shape of the structure, I can just generate an equivalent structure. That structure will give me the same deformed shape and the same moment diagram. So the equivalent structure will be something like that. So I'm just modeling the half of it because the other half will behave the same. So this part, the middle, it can move in the vertical direction, but the rotation must be equal to 0. So I describe that behavior as follows. I'm putting a fixed roller here. So with that, I make sure that I define 0 rotation at the middle and a translation in the vertical direction. Now, I put the uniformly distributed load here. 12 kilonewton meters is the uniform distributed load. Now, let's solve it. This distance is now 3 meters. That distance is again 3 meters. Let's give some labels. Again, point A, point B, and the middle, I just name it as point D. Now I will be analyzing this structure instead of this one and see if we get the same result. Okay, the equivalent structure will give the same deformed shape as this one, as the original structure. Okay, now let's do discretization now. Remember that my aim is not to simplify the solution here. My aim is, by looking at the deformed shape, can I generate a simpler, a smaller model? Okay, So in that sense, I generated a equivalent structure where I have less members. So when I do the discretization, these are the nodes and members. Now I have a rotation here, theta b, and I have a translational degrees of freedom here, delta E, and I will be using modified equation for this member, A, B, and E. That's B. Okay, so these are the degrees of freedom, and I got 2 degrees of freedom here. Now let's draw the free body diagram. Member AB, pin support here. I have a uniform distributed load here. Now I have MBC, MBE, and here I got MEB, and here I have VEB, and on this side I got MBA. So let's write the equilibrium equation. My first equilibrium equation, I have a rotational degrees of freedom at B. So I'm looking for a moment equilibrium equation at B. So sum of moments at B equal to 0, which tells me that MBA plus MBE must be equal to 0. That's my first equilibrium equation. And I have a translational degrees of freedom at E. So I need a force equilibrium. So sum of forces at Y at E must be equal to 0. So this tells me that the shear force EB must be equal to 0. And that's my second equilibrium equation. Now let's write down the slope deflection equations now. I'll start from member AB. So MBA, I'm using the modified equations. So 3EI over 3 theta B minus phi. No member loading, so no fixed moment, and this is equal to 0. These two cancel each other, and this one is equal to EI times theta B. Now let's work on member BE. So that's the initial configuration. We said that this will move in the upward direction. That's delta E. And I have a quarter rotation that's equal to phi angle. And phi is equal to delta E divided by 3. And phi angle is in counterclockwise direction, so that's a positive quarter rotation. Now let's write down MVC. That's equal to 2EI. Length is 3. So I got 2 theta B minus 3 phi. So it's 3 times delta E over 3. So this is equal to delta E. And the fixed moment is 12 times 3 squared over 12. And then I got MBC as equal to 4EI over 3 theta B minus 2EI over 3 delta E plus 9. Let's write down MCB. That's equal to 2EI over 3. This is not C, by the way. These are all E. Let me correct that. MEB is equal to 2EI over 3. Theta B minus delta E. And this time the fixed amount will be equal to minus 9. And then that would be equal to 2EI over 3 theta B minus 2EI over 3 delta E minus 9. So these are the two moment equation. I also need to calculate what VEB is. So in order to do that, I'm taking moment with respect to point B. So VEB times 3 plus MBE plus MEB minus the moment due to the distributed load should be equal to 0. Then in that case, VEB is equal to 1 over 3 minus MBE minus MEB minus 12 times 13 times 1 point. It's not 13, it should be 3, I'm sorry. 12 times 3 times 1.5. And if you put what MBE and MEB is, we find out VEB as equal to minus 2 over 3 EI theta B plus 4 EI over 9 delta B plus 18. And that's the shear equation that we get from member BE. Now I will write down the equilibrium equations and try to figure out the values of the unknown degrees of freedoms. The first equilibrium equation is MBA plus MBE equal to 0. This will give me my first equilibrium equation, which is equal to 7EI over 3 theta B minus 2EI over 3 delta B equals to minus 9. That's our first equilibrium equation. Now for the second equilibrium equation, we said that VEB equal to 0. So I got minus 2EI over 3 theta B plus 4EI over 9 delta B equal to minus 18. That's my second equilibrium equations. I got two unknowns, two equations. Now the solution. Let's write again everything in matrix form. EI parentheses 7 over 3 minus 2 over 3 minus 2 over 3 4 over 9 theta B delta B, and that's equal to minus 9 and minus 18. And when you solve it, you obtain theta B as equal to minus 27 over EI, and delta B, not delta B, delta E as equal to minus 81.2 divided by EI. Let me correct these. Keep writing delta B. These are not B, these are all delta E's. And as you see, if if you compare your result with our previous solution, we exactly get the same display rotation value at B. Of course, you can argue that that's a longer solution. Yes, it's a longer solution, but our aim here is to show you when you have some ideas about the deformed shape of any structure, you can actually idealize it or simplify it by defining some boundary conditions with an equivalent structure that gives you the same deformed shape. If you correctly represent the deformed shape with the deformed shape of the original structure with the equivalent structure, you get exactly the same result. Okay, in our second example, again I take the same symmetrical frame. This time we apply a lateral load. Again, we already solved that, but this time I want to create an equivalent structure and then analyze it. Okay, so we said that this is a symmetric structure and lateral loading, but this doesn't look like a symmetrical loading. So the first thing that I will do is this. I will redraw the same structure. Since this is an axially rigid frame, drawing that 10 kilonewton load as this or like this doesn't matter, it will give the same result. Now when I look at this structure, I see a symmetrical frame with a symmetrical loading. Okay, now let's take a deformed shape. How does it deform? So I have two identical columns. I expect to have a, let me use the red color. I expect to have a deformed shape like that, exactly the same deformed shape at both columns. So we have rigid joints and the deformed shape of that beam should be like that. And again at the middle we have a symmetry axis. And whatever I see on this side, I see it reversed but the same on the other side. Okay, and if you think about it, the moment diagram, we expect to have a moment diagram like this. And here at the middle we have a zero moment. Again, the same logic. Whatever I see on this side, I should see that's the symmetry axis, the same diagram, but in the reverse direction on the other side. Okay. Again, this curvature is the same, but just with an opposite sign. This moment same, but with the opposite sign on the other side. So that's why at the middle I should have a zero moment. And again, if you think about it, at the middle, this delta must be equal to 0. So with all this information in our hands, I can now generate an equivalent structure so let me draw the column first. I'm modeling it to the middle. Now here, this point cannot move in the upward direction, but it's free to rotate. So I can just represent that behavior with a pin support. And again, I got 5 kilonewtons here. Now this will be my equivalent structure. That's 3 meters. And again, I model the middle beam till the middle. And let's put some labels. Again, that's point A, B, and point E. Now, instead of analyzing this structure, now I will work on this one. Now, let's do the discretization. So we have a node, member, and sorry, I make a mistake here. This is not a pin support because it should move in the horizontal direction. That should be a roller support. Now that's our equivalent structure. Sorry for that. So I put a roller support here, column, a pin support here. And I got 5 kilonewtons here. Again, if you think about it, now I have a determinate structure and I can directly analyze it by using the equilibrium equations. But again, I will use the slope deflection equation instead. So let's show the degrees of freedoms. I got theta b here. I got delta b here. Since this beam is axially rigid, I got the same delta b in here. I can use modified equation member AB. Again, I can use modified equation at member BE. So I have 2 degrees of freedom. Now let's write down the equilibrium equations. But before that, I have to draw the free body diagram. Let's draw the free body diagram first. Then write the equilibrium equation. A roller support here, column, and applied loading is a nodal load this time, and magnitude is 5 kilonewtons. I got MBC here, and I got MBA here, and the shear force is VBA. Now, equilibrium equations. I have a rotational degrees of freedom at B, so sum of moments at B must be equal to 0. This tells me that MBA plus MBC must be equal to 0. That's my first equilibrium equation. And for the second one, I'll transfer VBA to the node and write down the force equilibrium at node. Sum of Fx at B must be equal to 0. So this tells me that the magnitude of that shear force must be equal to 5. And that's my second equation. Now let's write the slope deflection equations. Let's do it for member AB first. So initially it was here, it moved by delta B amount. That's the chord rotation. Let's show it with an angle. That's the phi angle. Phi angle is in clockwise, so phi will be equal to minus delta B divided by 3. Then MBA is equal to modified equations 3EI over 3. I got theta B, this time plus delta B over 3. And this will give me, these 3's will cancel, EI theta B plus EI over 3 delta B. I also need to calculate the shear force. So if I take moment with respect to that point, 3 times VBA should be equal to MBA, or we can just say that VBA is equal to MBA divided by 3. So VBA will be equal to EI over 3 theta B plus EI over 9 delta B. Okay, now I have to write the slope deflection equations for member BE. then MBE is equal to modified equations again, 3EI over 3, and I got only theta B now, and this is equal to EI theta B. Now I can write the equilibrium equations. First equilibrium equation is the moment equilibrium at B, which tells me that MBA plus MBE must be equal to 0, and this will give me my first equilibrium equation, which is equal to 2EI theta B plus EI over 3 delta B equal to 0. First equation, sum of forces in X at B must be equal to 0. This tells me that the shear force should be equal to 5. And my second equilibrium equation is EI over 3 theta B plus EI over 9 delta B should be equal to 5. That's my second equilibrium equation. And my solution is, again, let's show everything in matrix form. EI 2, 1 over 3, 1 over 3, 1 over 9, theta B and delta B should be equal to 0 and 5. And if you analyze that, we obtain theta B as equal to minus 15 over EI and delta B as equal to 90 over EI. And as you see, by using an equilibrium equivalent structure, and we generate that equivalent structure by looking at the properties of the deformed shape and the moment diagram, and by analyzing this equilibrium equivalent structure, we obtain exactly the same result with our previous solution.